Hello everyone, I am Hunar Gupta, currently a PhD scholar at IIT Kanpur. I am a TA in the course Fundamental of Supersonic and Hypersonic Flow. Today we will review what was taught in the previous classes, and we will mainly review the problems related to first few weeks of the course. So we will discuss some problems. The first problem is compressibility of a gas is given by. The problems are taken mainly from the assignments, initial assignments which were done. The compressibility of a gas is given by A equal to minus 1 by B dou V upon dou P, B 1 by dou rho upon dou P, C V dou B upon dou P, and D 1 by rho A square. So we will see what is the compressibility first. Compressibility, which is denoted by tau beta, will tell you about the fractional change of specific volume of fluid element due to high applied pressure change. So what is tau beta? Fractional change in volume of a fluid element due to the high applied pressure change. So minus sign is there because if we apply the pressure, volume will decrease. That's why it is minus 1 by V dou V by dou P. This is the formula for compressibility. Now we know that V equal to 1 by rho, where rho is the density. So if we substitute the B here, then we will get minus rho dou 1 by rho upon dou P, and if we take its derivative, then it will be minus rho into minus 1 upon rho square dou rho by dou P, which will be nothing but 1 by rho dou rho by dou P. This is the another form. Now we know that dou P by dou rho is nothing but A square, speed up found. So we can substitute this here also. So we will get this equal to 1 by rho A square. So in the option, if we see it, the first option will be correct. This is from the definition. Second option will also be correct because we have converted specific volume to density, and D option will also be correct. So A, B and D are correct options. We'll see the next problem. The distance at which a shock is formed ahead of a blunt body immersed in a supersonic or hypersonic flow is called as A. Shock expansion wave distance, B. Displacement distance thickness, C. Shock standoff distance, and D. boundary layer thickness. So what will be the answer of this? It is a very straightforward question. So in this question it is asked, let's say there is one blunt body and there is some supersonic or hypersonic flow. Then there will be one rho shock which will be formed here. So the distance at which this rho shock is formed, let's say this is delta. So what is this delta called? this delta is called fork standoff distance. So answer will be C. Let's see the another question. If the distance at which a fork is formed ahead of a body for free stream Mach number m1 equal to 3 is d1 and for m1 equal to 5 is d2, then option A, d1 is less than d2, option B, d1 upon d2 equal to 5 by 3 to the power 3 by 2, C, d1 upon d2 equal to 5 by 3 to the power 1 by 2, and D, d1 is greater than d2. So before we have seen what is the fork standoff distance. So if let's say for m1 Mach number equal to 3, the fork standoff distance is d1, and for m1 equal to 5, fork standoff is d2. So what will be the relation of this? First thing is to know that the supersonic and hypersonic flow are fairly complex flow. So there is no any straightforward relation which can be found between this fork standoff distance for a body. So option B and D are wrong. Only possibilities option A and D. Now let's say there is one body and there is one buffer here, and this is the d1 distance, d1 or d2. So and this is the flow m1. If there is density ρ1 here and density ρ2 here, so we know that ρ2 is always greater than ρ1, and as m1 increases, this ρ2 will also increases. You can see from any other fork relations also, like normal fork, oblique fork, ρ2 will increase as we increase the free stream Mach number. So if free stream Mach number increases, then ρ2 will increase. So for a same mass flow rate to pass through the body, for different Mach number, let's say Mach number 3 and 5, for different same mass flow to pass through the body, for a higher density, the fork wave will be nearer to the body. So if fork wave is nearer to the body, it means distance is decreasing. So if we increase the Mach number, the fork standoff distance will decrease. So that's why d1 will be greater than d2. Option D will be the correct option. Now let's see the next problem. Mach number is defined as A, under inertia force upon elastic force. Option B, under elastic force upon viscous force. Option C, inertia force upon viscous force whole square. Option D, elastic force upon gravity force. So what will be its answer? Okay, we will see what is the Mach number. So Mach number is a non-dimensional number which tells about the domination of fluid particle inertial force over the elastic force. The elastic force of fluid flow is responsible for propagation of pressure wave across the medium. So Mach number is given by under inertial force upon elastic force. It was only asked in the problem. So it is under inertial force upon elastic force, which is option A, which will be the correct option. So let's say what is the inertial force? Inertial force is rho A upon rho A u square. Elastic force is K into A. K is the modulus of elasticity and A is the area. And one thing I forgot to tell before, that inverse of compressibility also known as bulk modulus. So if we take the inverse of this K, then we will get the bulk modulus. So what is K? K equal to rho A square. K equal to 1 upon tau beta, which is nothing but rho A square. So we can directly substitute it here. This Mach number is given by this. A will cancel, so it will get under rho U square. And what is K? K is rho A square. Rho will cancel and we will get U upon A, where A is the speed of sound. Let's see the next problem. That is a conceptual problem. The specific internal energy of a gas is comprised of the following energy modes: A. Gravitational potential energy, B. Vibrational energy, C. Rotational energy, and D. Translational energy. So what are the energy modes which are present for the gas? For a gas, there are 4 types of energy mode. One is translational energy, another is rotational energy, vibrational energy, and electronic energy. So in this problem we see this translational, rotational and vibrational all are the energy modes of specific internal energy. Gravitational potential energy is not an energy mode. One thing to note is that all these modes will be present when for the molecules. For an atom, this rotational energy and vibrational energy will be 0. Let's see another problem. Thermally perfect gas has A. Cp and Cv constant, B. Cp is a function of temperature and Cv is also a function of temperature, C. Cp and Cv are function of pressure and temperature, D. None of the above. So perfect gas are mainly 2 types: calorically perfect gas and thermally perfect gas. For calorically perfect gas, the Cp and Cv are constant, and for thermally perfect gas, Cp and Cv are function of temperature. There is also one more type of gas, which is chemically reacting gas mixture. In which Cp and Cv both are function of pressure and temperature. So in this problem, it was asked about the thermally perfect gas. So for thermally perfect gas, both are function of temperature. So option B is the correct. Let's see the next problem. dE equal to minus P dV is applicable for A. Reversible adiabatic process, B. Isobaric process, C. Isothermal process, D. Isentropic process. So first see the first law of thermodynamics. Del Q equal to del Q plus del W equal to del E, and del W is nothing but minus P dV for reversible process. For reversible process, del W is minus P dV, and if the process is adiabatic also, then del Q equal to 0. So what will be del E equal to minus P dV. And reversible adiabatic process is also called isentropic process. So this will be applicable for isentropic process also. So option A and D will be the correct option. Let's see the next problem. Entropy associated with a thermodynamic process can increase due to the following effect or effects. A. Viscosity, B. Chemical equilibrium, C. Thermal conductivity, D. Mass diffusion. So all kind of effects which are responsible for non-reversibility are associated with increase in entropy. So viscosity, thermal conductivity, and mass diffusion all are related to non-reversible processes. That's why this following can increase the entropy. Chemical equilibrium. During the chemical equilibrium, it is in the state of equilibrium. So the forward reaction rate and backward reaction rate are equal, which is kind of, you can say, reversibility effect. So for chemical equilibrium, it will not increase the entropy. Aerodynamic heating at hypersonic speeds is observed. A. Near the nose region of a vehicle, B. In the free stream, C. Boundary layer formed on the vehicle, D. Far downstream of the body. What will be the answer for this problem? So if you see the near the nose region of the vehicle, what happened that we have seen before, that way this is the nose region of the body. Due to the hypersonic speed, there will be one bow shock will form here. So due to this bow shock, the flow will kinetic energy of the flow will be converted to thermal energy of the flow behind the shock wave. So due to this thermal energy, there will be aerodynamic heating near the nose region of the vehicle. Now if you see this free stream, in the free stream there is no aerodynamic heating. So So near the nose of the vehicle there will be aerodynamic heating, but not in the free stream. If you see the boundary layer, what happens at the boundary layer? At the boundary layer, the flow velocity, flow will encounter, flow will be affected by the viscosity inside the boundary layer. So due to the viscosity at the wall or at the body, the flow velocity will be zero. So if you see at the hypersonic speed, the flow velocity will be decreased from high velocity to almost zero near the body. So you can say the high amount of kinetic energy is converted to thermal energy. So due to which there will be aerodynamic heating inside the boundary layer of the vehicle. Far downstream of the body there will be no aerodynamic heating. Mainly aerodynamic heating will be observed near the nose region of a vehicle and boundary layer form of the vehicle. There are many other characteristics of hypersonic speed which are also related to the boundary layer, like viscous dissipation, which we already told now. Pressure coefficient on the windward CPW and leeward surface CPL of a flat plate placed in a Newtonian flow at 7-degree angle of attack are respectively equal to A. CPW equal to 0.1, CPL equal to 0.05, B. CPW equal to 0.03, CPL equal to 0, C. CPW equal to 0.05, CPL equal to minus 0.1, D. CPW equal to 0.05, CPL equal to 0.05. So this problem is related to Newtonian flow. So first we will see what is the Newtonian flow. Let's say there is one flat plate which is kept in the free stream at an angle theta. So we have to find what is the Cp on the body. So Cp will depend on what is the normal force which is acting on the body. So we have to find that pressure only. So first we will find what is the force which is acting normal to the body. So what will the change in the velocity in the normal direction? If we first let's see what is the normal direction velocity. It will be V infinity cos theta. Sorry, V infinity sin theta. And it is assumed that when the flow will flow velocity normal to the plate will become 0. For the change in velocity normal direction will be V infinity sin theta. And what will the mass flux component normal to the surface will be rho infinity A into V infinity sin theta. Area A is the area of the plate and rho infinity is the free stream density. So this is the mass flux. And what is the rate of change of momentum in normal direction? Mass flux into change in velocity, m into delta v. So m is rho infinity V infinity A sin theta and delta v is V infinity sin theta. If you multiply both, it will give rho infinity A V infinity square sin theta. And this rate of change of momentum in normal direction is nothing but force. If we divide this force by area, we will get the pressure, which will be equal to rho V infinity sin square theta. And this is no, and this pressure will be equal to P minus P infinity, because in calculating that it was the effect of free stream pressure is already considered here. So P minus P infinity equal to rho B square sin square theta. And what is the Cp? Cp equal to P minus P infinity upon half rho V square, which will be equal to 2 sin square theta. So Cp equal to 2 sin square theta. This will be the value of Cp. Now in the problem, there is one plate which is kept at angle theta equal to 7 degree. And this is the windward direction and this is the leeward direction. So Cpw, which we have already seen from the formula, it will be 2 sin square theta, which is nothing but 2 sin square 7 degree. So if we keep this value in the calculator, it will get 2 into 0.1219 square. So it will get 0.0297, which will be approximately equal to 0.03. And as in the leeward direction there is no flow, then CPL will become equal to 0. So what will be the answer? CPW equal to 0.03 and CPL equal to 0. So option B will be the correct. Let's see the next problem. The difference between thermodynamic and mechanical pressure is given by A, mu del dot B vector, B, mu bulk del dot B vector, option C, delta plus 2 by 3 mu del dot B vector, option D, mu bulk del dot B vector whole square. So first we have to see what is the mechanical pressure. So mechanical pressure is given by P bar equal to minus 1 by 3 sigma xx plus sigma yy plus sigma zz, and sigma ij is given by minus P del ij plus tau ij plus lambda kk del kk dou u kk upon dou x kk. In simplified form, for Newton's flow, Newtonian flow, it will be equal to minus P del ij plus tau ij is equal to mu dou ui upon dou xj plus dou uj upon dou xi plus del ij lambda del dot e. So let's find out what is sigma xx. Sigma xx is, if we keep I equal to I. First let's find sigma ii, because here only both are same. So sigma ii equal to minus P del ii plus mu dou ui upon dou xi plus dou ui upon dou xi plus del ii lambda del dot b. Which will be equal to minus P del ii plus mu equal to mu dou ui upon dou xi plus lambda del ii del dot B. So what will you get? Sigma xx equal to minus P. One more thing. Okay, I will write now. Minus P dou xx is 1 plus 2 mu dou ux upon dou x or I will write one thing, B vector equal to u I k plus v j k plus w k k. For here instead of ux I will write directly e plus lambda del dot v. Similarly, sigma y by equal to minus p plus 2 mu dou b by dou y plus lambda del dot v, and sigma z equal to minus p plus 2 mu dou w upon dou z plus lambda del dot v. So their sum will be sigma xx plus sigma yy plus sigma zz equal to minus 3p plus 3 plus 6 mu dou u by dou x plus dou v by dou y plus dou w by dou z plus 3 lambda del dot v. I will write it here. So what we got, this dou u by dou x plus dou v by dou y plus dou w by dou z is nothing but del dot v. So we will get sigma xx plus sigma yy plus sigma zz equal to minus 3p plus 6 mu del dot v plus 3 lambda del dot v, or we can get p bar equal to minus sigma xx plus sigma yy plus sigma zz upon 3. So if we divide it by minus 1 by 3, we will get this as p minus p minus 2 mu plus lambda one mistake I have made. This is not 6 mu, this is 2 mu. Because we will get 2, we are keeping 2 mu common. So here also it is 2 mu. So we will get 2 mu by 3 plus lambda del dot b. If we take both of these difference, p minus p bar equal to lambda plus 2 mu by 3 del dot b. This lambda plus 2 mu by 3 is also called bulk viscosity, mu bulk del dot b. So our answer will be option B, mu bulk del dot b, or option C, lambda plus 2 mu by 3 del dot b. This is the difference between thermodynamic and mechanical pressure. This P is simply the thermodynamic pressure. Now we see the next problem. Two-dimensional flow velocity field is given by v vector equal to phi by q I cap minus x by 2 j cap. Statement 1. This equation is sufficient to represent the conservation properties of an incompressible viscous fluid flow. Statement 2. It satisfies the incompressibility condition. First we will see the second statement, incompressibility condition. So what is the incompressible condition? Del dot V should be 0. So we will find what is del dot V. So what is del dot V? I dou y dou x. Sorry. Del dot V is dou u dou x plus dou v dou y. Here you can see that 5 by q is u and v is minus x by 2. So dou u dou x will be 0 and dou v dou y will also be 0. So this is nothing but 0. So it is satisfying the incompressible condition. So statement 2 is true. But one thing to know is that it is satisfying the incompressible condition. It means it is satisfying the continuity equation. But to satisfy the conservation properties of incompressible viscous fluid flow, there is also momentum equation also there. So we don't know if it will satisfy the momentum equation or not. So this equation is not sufficient to represent the conservation properties of an incompressible viscous fluid flow. So that's why this statement 2 will be false. So there are 4 options and option B is the correct one, in which is statement 1 is false and statement 2 is true. We'll see the next problem now. In Newtonian fluid, the expression for sigma xx plus sigma yy upon 2 is given by. So before we have seen that sigma ii was given by this. Now it was given by, and in this problem there are 4 options also. A minus 2p plus 2 mu dou u dou y plus dou v dou x plus 2 lambda del dot b. B minus p plus mu dou u dou y plus dou v dou x plus lambda del dot v. C minus p plus mu dou u dou x plus dou v dou y plus lambda del dot b. D minus 2p plus 2 mu dou u dou x plus dou v dou y plus 2 lambda del dot v. So we have derived equation for sigma ii, which was minus p plus 2 mu dou ui upon dou xi plus lambda del dot b. This is statement sigma ii. If lambda ii is 1, so I have directly removed it. Or you can write also minus p then ii then I. Okay. So sigma xx is what? Minus p plus 2 mu dou u dou x plus lambda del dot b. Similarly, sigma yy is given by minus p plus 2 mu dou vy dou x dou vy dou y plus lambda del dot b. So sum of these two will be sigma xx plus sigma yy equal to minus 2p. We'll take 2 common, minus 2p plus mu dou u by dou x plus dou v by dou y plus lambda del dot v. If we divide it by 2, then we get sigma xx plus sigma yy upon 2 equal to minus p. Only 2 I have taken common. Minus p plus 2 dou u by dou x plus dou v by dou y plus lambda del dot b. If we see from the option C is the correct one. Now we'll see the next problem. A pressure field is expressed as P x y z equal to 4x square plus 2y square minus 6z square. The expression for del P for pressure field is given by A 16x square I cap plus 4y square j cap minus 36z square k cap. Option B 4x I cap plus 2y j cap minus 6z k cap. Option C 8x I cap plus 4y j cap minus 12z k cap. Option D 4x I cap plus 8y j cap plus 6z k cap. So how is the del P is given by? Del P is nothing but I dou P by dou x plus j dou P by dou y plus k dou P by dou z. We know that P is 4x square plus 2y square minus 6z square. So what will be dou P by dou x? Dou P by dou x will be 8x. What will be dou P by dou y? It will be 4y. And dou P by dou z, it will be minus 12z. We substitute this value in the del P, then we will get del P equal to 8xi plus 4yj cap minus 12z k cap. And let me match it with option C 8xi cap plus 4yj cap minus 12z k cap. We'll see the next problem. If an incompressible velocity field is given by v vector equal to p x cube I cap plus q y cube j cap, the ratio of p and q is given by a x upon y, b x upon y whole square, c minus y upon x, option D minus y square upon x cube. So for incompressible velocity field, what is the condition for incompressibility? We have already seen before. It will be del dot B equal to 0. So what will be this value? Dou u by dou x plus dou v by dou y equal to 0. In the above problem, it is given v vector equal to p x cube I cap plus q y cube j cap. So here u equal to px cube and v equal to qy cube. So dou u by dou x will be 3px square and dou v by dou y will be 3qy square. if we put in this incompressibility condition, we'll get 3px square plus 3qy square equal to 0, or simply px square plus qy square equal to 0. We'll take this q term on the right hand side. We'll get px square equal to minus qy square. If we divide this equation by q, we'll get p by q equal to minus y square upon x square. So what will be the answer? This will be option D, minus y square upon x square. We will see the next problem. Following is or are the correct attributes of acoustic waves. Option A, weak pressure waves. Option B, they propagate at the local sonic speed. C, they propagate at the local velocity of the flow only. D, they are the linear waves. So, if you know about the acoustic waves, this question is very straightforward, and this is a conceptual question. So, what will be the properties of the acoustic waves? First one is true, because acoustic waves is weak pressure waves, and these weak pressure waves move with the local sonic speed. Means a equal to m equal to 1. They have Mach number of equal to 1. And if they are propagating at local sonic speed, they cannot propagate with the local velocity of the flow. Option C is wrong. And they are the linear waves. So option A, B and D are the correct option. Okay, now let's see the next problem. If the initial velocity distribution is given as follows. This is the initial velocity distribution which is given. From 0 to x equal to 1, velocity is increasing. And from x equal to 1 to till for each value of x is greater than 1, e equal to 1. And the governing wave equation is dou u by dou t plus u dou u by dou x equal to 0. I have not taken the full question here. So in this problem, we have to tell what kind of wave will form. What kind of wave formation will occur. After some time. So at t equal to 0, this velocity distribution is given. So we'll draw the characteristics line, and the characteristics are given by dx by dt equal to u. So if you see the first characteristic line, velocities is 0 at x equal to 0 initially. So velocity is 0 at x equal to 0. Then if you see the velocity is steadily increasing. And x equal to 1, after x equal to 1, these are constant. So dx by dt at t equal to 0 will be 0 for x equal to 0, and dx by dt t equal to 0 will be equal to 1 for x is greater than or equal to 1. So if you see this characteristics line, what kind of wave these will form? These are uh, moving away from each other. All these characteristics line are moving away from each other. So what are this characteristics line form? Expansion fan. So as we move, so this kind of wave, so the kind of wave formation will be of expansion fan. This motion will form the expansion wave. Now let's see the next problem. If Cv of the air is 5 by 2 r, find the degree of freedom. Option A 2, option B 5, option C 3, and option D equal to 4. So for degree of freedom is given by n, and the formula of n is gamma equal to 1 plus 2y n. So for finding n, we should first find gamma, and gamma is nothing but Cp by Cv. So we have to know what is the Cp first. Cv is given by 5 by 2 r, and Cp will be given by Cv plus r. So Cp will be equal to 5 by 2 r plus r equal to 7 by 2 r. Hence the ratio gamma equal to Cp by Cv will be nothing but 7 by 2 r upon 5 by 2 r, which will be equal to 7 upon 5, which will be 1 plus 2 upon 5. And this gamma is nothing but 1 plus 2y n, which is nothing but 1 plus 2 upon 5. If you solve this, you will get n equal to 5. So 5 will be the degree of freedom, which is option B. Now let's see the next problem. Flow past two ranges P and Q would be similar for the following combination, where mi and theta I represent the free stream Mach number and wave angle respectively. Option A, mp equal to 8, theta p equal to 3 degree, and mq equal to 10, theta q equal to 4 degree. Option B, mp equal to 10, theta p equal to 5 degree, and mq equal to 11, and theta q equal to 6 degree. C, mp equal to 9, theta p equal to 4 degree, and mq equal to 12, and theta q equal to 3 degree. Option D, mp equal to 12, theta p equal to 4 degree, and mq equal to 16, and theta q equal to 3 degree. So for the hypersonic flow and for the cylinder body, the flow will be similar only if hypersonic flow similarity parameter is same. So what is the hypersonic similarity parameter? It is given by K, and it is the product of Mach number and wave angle theta. So if m into theta is same, then flow will be the similar. So for the two waves P and Q, the multiplication of mp theta p should be equal to mq theta q. So for the first option, mp theta p will be equal to 24, and mq theta q is 40. So both are not same, so both flow will not be similar. Option B, mp theta p is equal to 50, mq theta q is equal to 66. Both are not equal, so the flow is also not similar. Option C, mp theta p equal to 36, mp theta p is equal to 36. Both are equal, so flow will also be similar. Option D, mp theta p equal to 48, mq theta q is 48. So here also mq theta q, m into theta product, that means hypersonic similarity parameter is same, that's why flow will be the similar. So answer for this problem is option C and D. Let's see the next problem. The following are the false statements regarding the normal form. Option A, rho naught 2 is less than rho naught 1. Option B, P naught 2 equal to P naught 1. Option C, T2 is greater than T1. Option D, M2 is greater than M1. So let's see the different normal shock. This is upstream flow, which is given by 1, and this is downstream flow, which is given by 2. Their properties are M1, T1, rho 1, rho naught 1, P naught 1, P1, and in the downstream it is M2, T2, rho 2, P naught 2, rho naught 2, P2. So we should know that T2 is always greater than T1, temperature increases, pressure also increases, density also increases, but total pressure decreases, total density decreases, and Mach number also decreases. So option A, if you see rho naught 2 is less than rho naught 1, it means total density is decreasing, which is the correct option. But you have to find a false statement, so this will be the wrong option. Option B, P naught 2 equal to P naught 1, but this is not true. P naught 2 is less than P naught 2, so this is a false statement and correct option for this problem. Option C, T2 is greater than T1. This is the true statement, but it is not false for regarding the normal shock, so this is also not correct. Option D, M2 is greater than M1, but M2 decreases for normal shock, so this is the false statement regarding the normal shock, so this is also correct option. So option B and D are the correct options. Let's see the next problem. Following are the two statements regarding a normal shock. It is same as previous question, only the statement we should tell is the true statement. Option A, P2 is greater than P1. Option B, P1 is greater than P2. Option C, S02 equal to S01. And option D, rho 2 is less than rho 1. We already saw that pressure density increases across the P2 is greater than P1 and rho 2 is greater than rho 1 for the normal shock. So option D will be the wrong, option B will be wrong, and option A will be the correct. One more thing is H01 will be equal to H02 for normal fog. How? Due to the energy conservation. So option C is also correct option. Let's see the next problem. On a two-dimensional flat plate parallel to the x-axis, if there is mass transfer at the wall due to the ablation or translational cooling, this is for maintaining a surface at a safe temperature while it is under the influence of aerodynamic heating. The wall boundary condition would be given by nomenclature. UW is a specified velocity tangential to the surface, and VW is the specified velocity normal to the surface. Option A, U equal to 0, V equal to VV, VW. Option B, U equal to UW, V equal to VW. Option C, dou U upon dou Y equal to 0, V equal to VW. Option D, U equal to 0 and dou V upon dou Y equal to 0. So what is the answer for this problem? Okay, so in this problem there is one flat plate, and from this flat plate normal to this mass transfer is happening due to the ablation or translational cooling. So velocity of this normal velocity is UW. So for the ball boundary condition, what should be the boundary condition? We know that one thing, this is the x direction, this is y direction. So V velocity will be what? VW due to this cooling. This is the true. So option D is already wrong. One more thing, if there is viscous effect is there, then there will be no slip boundary condition. There will be no slip on the body. So U will be equal to 0. So option A will be the correct option. Option B and C are wrong. Now let's see the next problem. A high-speed flow meets a flat plate. A compressible boundary layer forms on the plate. The external flow occurring beyond the compressible boundary layer is A. Always colder than the wall. Option A. Always colder than the wall. Option B. Always hotter than the wall. Option C. Invisible. Option D. Viscous. One thing to note that we cannot tell if it is colder or hotter always, because it depends on many conditions, like what is the temperature of flat plate, what type of boundary conditions are there. So these two options will be wrong. Now in this problem it is given that on the flat plate there is compressible boundary layer, high speed flow is there. So we already know that most of the viscous effect will be inside the boundary layer. So outside the boundary layer, this is which is beyond the boundary layer, the flow which is beyond the boundary layer, the effect of viscosity will be very negligible and is considered invisible only. So the true option will be option C, and there will be no viscosity effect will be there. So option C is the correct option. Now let's see the Another problem. The significant similarity parameter in a compressible boundary layer is what are? Option A, Reynolds number. Option B, Mach number. Option C, Prandtl number. Option D, ratio of the specific heat. So what will be the option? Reynolds number is given by RE. Mach number is given by M. Prandtl number is given by PR. And specific ratio of specific heat is given by tau. If you have seen the skin friction coefficient, it was dependent on this Reynolds number, Mach number, Prandtl number, gamma, and TW by TE, these kind of parameters. So you can see that all these parameters are important parameters, which is used for the similarity. So all four of them are correct in this case. Let's see the next problem. In the transformed compressible boundary layer equation, G equal to H by He and dou F upon dou eta equal to U by Ue. The following is or are appropriate boundary conditions. Option A, at eta equal to 0, F dash equal to 1, G equal to G wall for isothermal wall. At eta equal to infinity, F dash equal to 0 and G equal to 0. C, at eta equal to 0, F dash equal to 0, G dash equal to 0 for adiabatic wall. D, at eta equal to infinity, F dash equal to 1 and G equal to 1. So let's say for eta equal to 0. For eta equal to 0, U will be equal to 0 due to the slip boundary condition. So if U is equal to 0, then dou F upon dou eta, it means F dash will be equal to 0. So option A, where for eta equal to 0, F dash equal to 1 is given, is wrong. And now option C, that is given for adiabatic wall. For adiabatic wall, let's say G dash, that means dou G by dou eta, which will be given by 1 by He dou H upon dou eta, which is nothing but 0. For adiabatic wall, dou H upon dou eta is 0. So G dash is nothing but 0. So option C is the correct one. Now let's say for eta tends to infinity, U will be equal to Ue, which means F dash will be equal to U by Ue equal to 1. So F dash is equal to 1 at eta tends to infinity, it means option B is wrong. And one more thing, this H will also be equal to He, which means G, which is equal to H upon He, will also be 1. So F dash and G both will be equal to 1. So option D is also correct. Now let's see the next problem. A gas has a molecular weight 32 kg by kilomole. Its specific gas constant is, you have to find a specific gas constant R. Okay, let's say this, I denote this universal gas constant by R bar. Okay? R bar equal to 8314 joule per kilomole Kelvin. This is universal gas constant. And molecular weight I will denote by m bar, which is 32 kg per kilomole. So R will be equal to R bar upon m bar. R bar is 8314 upon 32. So if you divide it in the calculator, you will get 259.812 joule per kg Kelvin. Which is approximately equal to 260 joule per kg Kelvin. So option A is the correct option. Let's see the next problem. The total pressure of a reacting gas mixture is 2.65 atmosphere. There are 5 species and the partial pressure of the first 4 species are 0.55 atmosphere, 0.35 atmosphere, 0.636 atmosphere and 0.28 atmosphere respectively. The partial pressure of the fifth species is option A 1.11 atmosphere, option B 1.27 atmosphere, option C 0.96 atmosphere, option D 0.73 atmosphere. So there are total 5 species, 1, 2, 3, 4, 5, and first species partial pressure is 0.55 atmosphere, second has 0.35 atmosphere, third has 0.36 atmosphere, fourth has 0.28 atmosphere, fifth pressure we have to find, and the gas mixture pressure P is given as 2.65 atmosphere. So as we know that the gas mixture pressure is sum of all the partial pressure of its species, which is nothing but P1 plus P2 plus P3 plus P4 plus P5. So P1 is, if we put all the value, 0.55 plus 0.35 plus 0.36 plus 0.28 plus P5. And the sum and the P pressure is 2.65. So this 2.65 will be equal to, if we take the sum of all these pressure, it will be equal to 1.54 plus P5. So P5 will be equal to 2.65 minus 1.54. Which will be equal to 1.11 atmosphere. So the partial pressure of the fifth species is 1.11 atmosphere. Let's see the next problem. In a rocket engine, the fuel is H2 and oxidizer is O2. The following equilibrium chemical reactions take place in the engine. 1/2 H2 gives H, 1/2 O2 gives O, H2 plus O gives OH plus H, OH plus H gives H2O. The ratio of number of hydrogen nuclei to the number of oxygen nuclei per unit mass of the mixture is given by option A, pH square whole square plus pH plus pH2O whole square plus pOH upon PO2 whole square plus PO plus pH2O whole square plus pOH. Option B, pH2O plus pH plus pH2O plus POH upon PO2 plus PO plus pH2O plus POH. Option C, 2pH2 plus pH plus 2pH2O plus POH upon 2PO2 plus PO plus pH2O plus POH. Option D, half pH2 plus pH plus half pH2O plus POH plus half PO2 plus PO plus PPH2O plus POH. So in this problem we have to find what is the number of hydrogen nuclei and ratio of number of hydrogen nuclei to the number of oxygen nuclei per unit mass of the mixture. Okay. So one thing to know is that for here we have total 4 species: H2, O2, H2, 4 molecule, H2, O2, H2O and OH. But species we have also H and O also. So total 6 species we have. So one thing to know is that 1 mole of H2 will give 2 mole of H. Or you can say that 1 H2 molecule will have 2 H molecule, 2 H nuclei. Similarly, 1 H2O will have 2 H nuclei. 1 OH molecule will have 1 H nuclei, and 1 H species and one H will have only 1 only. So let's say the eta I is the mole mass fraction of species I. Then number of hydrogen atom will be ratio of hydrogen atom upon Avogadro number. This is the Avogadro number. Equal to 2 this ratio and is given per unit mass. So that's why we will take the mole mass ratio 2 eta H2O, because in H2O, in one molecule of H2 there are 2 H2 hydrogen nuclei, 2 eta H2O plus 2 eta H2 plus eta OH plus eta H. Similarly, NO upon Na, it will become equal to 2 eta O2 plus eta H2O plus eta O plus eta OH. If we take the ratio of these two, then NH upon NO will become equal to 2 eta H2O plus 2 eta H2 plus eta OH plus eta H upon eta H2O plus eta O2 eta O2 plus eta OH plus eta O. Now we also know that Pi V equal to eta I R T. So this eta I is proportional to Pi. So we can replace this eta I by Pi because V, R bar, T are constant for each cases. So we will get NH upon NO equal to 2 PH2O plus 2 PH2 plus POH plus PH upon PH2O plus 2 PO2 plus POH plus PO. Now we have to see which option is correct. On the numerator, H2O and H has 2 coefficient and OH and H has 1 coefficient. This square equation is wrong. In the option B, H2O and OH, H2 and H2 has not 2 coefficient, so B is also wrong. Option D also wrong because they have half of the H coefficient. Option C, 2 in the numerator, H2 and H2 has 2 coefficient and H and OH has 1. For the O2, for denominator, only O2 has 2, rest H2, OH and O has 1 coefficient. So only O2 has 2 and H2, OH and O has 1 coefficient. So option C is the correct option. So this option C is the answer. We will check. Now we will see the next problem. Mixture of reacting gas, perfect gases contain 3 species. The instantaneous mole fractions of 2 species are x1 equal to 0.35 and x2 equal to 0.27 respectively. The value of x3 is A 0.62, B 0.68, C 0.83, D 0.31. So one thing to know that the sum of all mole fraction is always equal to 1. So x1 plus x2 plus x3 is equal to 1. x1 is 0.35, x2 is 0.27 and x3 we have to find. So x3 will be equal to 1 minus sum of these two, 0.62 equal to 0.38. So 0.38 will be the answer. Let's see the next problem. If in a mixture of reacting perfect gases, the mole fraction and molecular weight of a certain species are 0.5, 0.45 and 28 units respectively. Then find the mass fraction of the species if the molecular weight of the mixture is 54 units. So mole fraction of one species, let's say I, is 0.45 and its molecular weight mi bar is 28 and molecular weight of the mixture is 54. So we have to find the mass fraction of the species. The mass fraction denoted by, let's say, Ci. So mass fraction of the species is mass of the species upon total mass. So let's say we divide it by molecular weight. Then it will become like this. We have divided numerator and denominator by the molecular weight of respective. So mi upon mi bar is xi, m upon m bar is x, and mi bar upon m bar. Sorry, not x. This is mole of this and total mole. So this is nothing but xi mi bar upon m bar. Xi is what? 0.45, mi bar is 28 and m bar is 54. So if we multiply it, we will get 0.233. So option C is the correct one. Let's check the next problem. In the mixture of reacting perfect gases, calculate the mixture molecular weight based on the table of the values below. There are three species, 1, 2, 3. Their mole fraction and molecular weight is given. So mole fraction of species 1, 2 has this y coefficient, so we have to find y first. For total, sigma xi equal to 1. So x1 plus x2 plus x3 equal to 1. x1 is y, x2 is also y, and x3 is 0.4. So their sum is 3y equal to 0.6 and y we will get as 0.2. So the value of xi will become 0.2, 0.4 and 0.4. And the mixture molecular weight is given by sigma xi mi bar. I am using bar everywhere for the molecular weight. So sigma 0.2 into, sorry, not sigma. We will write for each species 0.2 into 20 plus 0.4 into 30 plus 0.4 into 40. So if we simplify it, then we will get 33, and option C will be the answer. So today's class we have solved the question related to first few weeks, and these were the assignment problems which were given for the assignment. And today we will stop our class for today, and next week on the Wednesday will be the last live session which will cover the week 12th. So see you in the next class. Thank you.